The universe is full of mysteries. From the vastness of space to the tiniest particles, there are countless questions that baffle even the brightest minds. One of the biggest is the question of why we exist. Why is there something rather than nothing? This question has puzzled scientists and philosophers for centuries. After all, the Big Bang should have created equal amounts of matter and antimatter. In theory, these two should have annihilated each other completely, leaving behind a universe filled with nothing but energy. These particles annihilate each other upon contact. When matter and antimatter meet, they destroy each other in a burst of energy, a process that should have left our universe empty. So, a universe filled with equal parts matter and antimatter shouldn't exist, yet here we are, living in a universe dominated by matter. This paradox is one of the greatest puzzles in modern physics. This mystery is called the Matter-Antimatter asymmetry. It suggests that somehow there was a slight imbalance in the amounts of matter and antimatter produced in the early universe. Scientists have long sought an explanation. They have conducted countless experiments and proposed numerous theories to understand this imbalance. Recently, physicists made a breakthrough that brings us closer to an answer. By studying the behavior of subatomic particles in high-energy experiments, they have uncovered new insights into the forces that shaped our universe. These discoveries are helping to piece together the cosmic puzzle. They reveal that the laws of physics may have subtle differences when applied to matter and antimatter, leading to the slight excess of matter that makes up our universe. The journey to understand matter-antimatter asymmetry is far from over. Each new discovery opens up more questions and avenues for research, pushing the boundaries of our knowledge. As we continue to explore these fundamental questions, we inspire the next generation of scientists. They will carry forward the quest to unravel the mysteries of the cosmos. The universe is a vast and wondrous place, full of secrets waiting to be discovered. With each step forward, we come closer to understanding our place in the grand cosmic puzzle.
The breakthrough involves a rather unusual molecule radium monofluoride, or RAF. Radium is a radioactive element with a large asymmetric nucleus. This asymmetry makes RAF sensitive to subtle effects that violate fundamental symmetries in physics. These violations could hold the key to understanding the matter-antimatter asymmetry. To unlock this secret, physicists needed to study the quantum structure of RAF in detail.
Studying a molecule like RAF is no easy task. The complexity of its structure and the challenges posed by its properties make it a formidable subject for scientific inquiry. It's radioactive and exists in very small quantities. This means that researchers have to handle it with extreme care, using specialized equipment and protocols to ensure safety and accuracy. To overcome these challenges, physicists used a combination of ion trapping and laser cooling. These advanced techniques allow scientists to manipulate and study ions in ways that were previously impossible. First, they created RAF ions, which are atoms that have gained or lost electrons. This ionization process is crucial because it changes the properties of the atoms, making them easier to control and study. They then trapped these ions using electric fields. These fields create a sort of cage that holds the ions in place, preventing them from moving freely. This allowed them to hold the ions in place for study. By confining the ions, researchers can observe their behavior and properties in a controlled environment. However, the ions were still moving too fast to study their quantum structure in detail. The rapid movement of the ions makes it difficult to capture precise measurements and observations. To address this, scientists employed laser cooling techniques. By directing laser beams at the ions, they were able to slow down their movement significantly. This cooling process is essential for studying the quantum structure of the ions. With the ions moving more slowly, researchers can take more accurate measurements and gain deeper insights into their properties. The combination of ion trapping and laser cooling represents a significant advancement in the field of molecular physics. It opens up new possibilities for research and experimentation, allowing scientists to explore the fundamental nature of matter in unprecedented detail. As technology continues to evolve, these techniques will become even more refined, leading to further breakthroughs and discoveries. The work being done today lays the foundation for the scientific advancements of tomorrow. In the end, the study of RAF and similar molecules not only enhances our understanding of the universe, but also drives innovation and progress in various scientific fields. The dedication and ingenuity of researchers pave the way for a brighter, more informed future.
To further slow down the RAF ions, physicists used laser cooling. This technique uses lasers to gently nudge the ions, reducing their kinetic energy and cooling them down. With the ions trapped and cooled, physicists could probe their quantum structure using lasers. By carefully tuning the laser frequency, they could measure the energy levels within the molecule. This provided a detailed map of RAF's quantum world.
Section 5. Symmetry violations and the imbalance of the universe. In this section, we delve into the fascinating world of symmetry violations, a topic that has intrigued physicists for decades. Symmetry, in its simplest form, is the idea that certain properties of a system remain unchanged under specific transformations. However, in the quantum realm, these symmetries can be broken, leading to profound implications for our understanding of the universe. The results of these measurements were exciting. They provided new insights into the fundamental forces that govern the universe. When scientists observed these symmetry violations, it was like uncovering a hidden layer of reality, one that challenges our conventional understanding of physics. They confirmed that RAF is indeed sensitive to effects that violate certain fundamental symmetries in physics. This sensitivity allows researchers to probe deeper into the mysteries of the quantum world, revealing interactions that were previously thought to be impossible or extremely rare. These symmetries, known as parity and time reversal symmetry, state that the laws of physics should be the same if we reverse the spatial coordinates or the direction of time. Parity symmetry involves flipping the spatial coordinates, like looking at a mirror image, while time reversal symmetry involves reversing the flow of time. In a perfectly symmetrical universe, these transformations would leave the laws of physics unchanged. However, these symmetries are not always perfectly obeyed in the quantum world. In fact, certain interactions, such as those involving weak nuclear forces, exhibit clear violations of these symmetries. These violations are not just theoretical curiosities, they have real-world implications, influencing the behavior of particles and the evolution of the universe itself. By studying these symmetry violations, scientists hope to unlock new levels of understanding about the fundamental nature of reality, potentially leading to groundbreaking discoveries in physics.
Section 6. Radium Monofluoride, a beacon in the search for new physics. The violations of parity and time reversal symmetry observed in RAF are tiny. However, they have profound implications for our understanding of the universe. These violations suggest that there are still undiscovered particles and forces at play. These unknown factors could be responsible for tipping the balance between matter and antimatter in the early universe.
Section 7. The Standard Model and Beyond. The current best description of particle physics is called the Standard Model. While incredibly successful, it cannot explain the matter-antimatter asymmetry or other observed phenomena like dark matter and dark energy. Physicists are searching for physics beyond the Standard Model. The study of RAF could offer a path forward.
Section 8. A future illuminated by radium monofluoride. The research on RAF is still in its early stages. However, it has the potential to revolutionize our understanding of fundamental physics. By studying RAF in more detail, we might unravel the secrets of the matter-antimatter asymmetry and uncover new laws of nature. The future of physics might be illuminated by this unusual molecule.
Section 9. Implications for our understanding of the universe. The implications of this research extend far beyond the laboratory. Understanding the matter-antimatter asymmetry is crucial for answering fundamental questions about the origin, evolution, and composition of the universe. The findings from the RAF experiments could lead to a paradigm shift in cosmology and astrophysics.
Section 10. The quest for knowledge continues. The search for knowledge is a never-ending journey. The breakthrough with RAF is a testament to the power of human curiosity and ingenuity. As we delve deeper into the mysteries of the universe, we are likely to encounter even more surprises. The future of science is bright, and the answers to some of the universe's biggest questions might just be one experiment away.